Okay, we'll wait for students to come here, and after they come, we'll start with our class. So yeah, we'll wait for 2 minutes. Mm. Hello.
Hello.
Yeah. Okay. Okay. We'll wait for 2 minutes and then we'll start. Okay.
Okay. Sure.
Mhm. Okay. Let us start. I don't think so. Any more students are coming right now. So yeah, I have started my recording. I will share my screen. Mhm. Can you see my screen, Daksh?
Yes, yes.
Okay. So today we will review concepts of uh, lecture 9, 10, 11, 12. 9 was on the electromagnetic fields, uh, EM fields. Here we learned that Maxwell's equation as well as the continuity equation. These are consistent with special relativity. What this means is that if you take your Maxwell's equation and the continuity equations, if you change the coordinates and coordinates as well as the uh, components of the four vectors which are there, the form of the equation do not change, right? This is what we checked in lecture 9, and lecture 10 was about yeah, lecture 10 was about the stress tensor. We found that there is a conserved quantity in these field theories, which is called the stress tensor, which is written as this. And when we use the Noether procedure to calculate the stress tensor, we get a Noether's process. Noether process gives antisymmetric, asymmetric stress tensor. We can add a term which is divergence less and make this stress tensor add S mu nu to this T mu nu and define a new stress tensor. This is a symmetric stress tensor. Because it satisfies this equation. This is what we saw in lecture 10. In lecture 11, it was more about Green's function. And Green's theorem. We learned how to solve the Poisson equation with Green's function method. And we also solved the Green's function with the Poisson. Yeah. And we wrote the solution for phi in the case of electrostatics. This came out to be something like this, right? Am I correct? And I think there was a 4 pi here. Yeah, and then we saw something called image problem. And one of the examples was worked out. If you have a ball, sphere, which is a conductor and it is grounded, and you have a charge outside, which is Q, you have to find the image charge. Here something, so QIM, which is inside. We use the concept of image charge because we want the surface of the sphere to be at V equal to 0 potential, since it is grounded. This was worked out, and this image problem was taken and it was used for any general configuration of conductors and it was found that the potential looked something like this Coulomb potential. plus is the surface of the conductors times potential at those places, the normal to the surface minus, am I right? This is what it was, right? And the configuration being conductors are somewhere like this, and they have some surface. Say these are conductor 1, conductor 2, conductor 3, conductor 4, conductor 5, and you want to find a potential at some R from the origin. This is the origin, suppose, in this. These are the surface enclosed by the conductors. This was in Green's function and Green's theorem. And we also saw an idea of this proof. We saw this rigorously of x. Yeah, these were the main points. And in the diffraction theory, which is the lecture 12, I guess, we explicitly worked out Kirchhoff and diffraction. We had a source which was giving off some monochromatic light, and we have an aperture here, and this goes to the screen and forms some diffraction patterns. We found the potential in this case, and also now to find the electric field and magnetic field, we just have to take the curl and the gradient of these things. Curl of A is equal to B, and gradient of phi minus del T of A will give you electric field. And from there, you find out what is, you may get something like E naught times some function of time, which will generally be cos omega t or something like this. And this E naught you are going to use in intensity, and you are going to get a intensity versus position R graph. Going to find that relation. And another limit, when the uh, distance between these two, if it is far away, then we'll obtain something called as Fraunhofer diffraction. We saw this much. So in those 4 lectures, we had these many ideas compressed. Right. So today we'll do some problems relating to these. I don't think so we will do any problem relating to diffraction theory because it's a direct derivation. And there you can take any, if you want to find, the phi r had some formula like this. Formula. What was it? D3x ix do g x minus naught del n This is yeah, I think this was the formula, right? You can put different phi x, different g's for the source, and you can find this is the source phi. So, and you can find this thing and calculate. We can work problems in that regard, but I don't think so. It is very required if you just know the derivation of at least this one, because these integrals may be very difficult to do. So let us start with EM fields, but a very simple case of it, which is the problem which I'll write to you now. So we have a Lagrangian L, and it is a charged particle. It's a Lagrangian for a charged particle. It is moving with some velocity with charge E under the influence of this magnetic field uh, with the potential phi x and A. Okay, where xi ai is equal to summation Week3. So a1, a2, a3 are some functions. Phi is some function. They are electromagnetic potentials actually, and uh, xi is the xi dot is the velocity of the ith component of the particle. The first thing to do is find Euler-Lagrange equations and write in terms of electric field and magnetic field. Okay, did you get the question, Daksh? Hello?
Yes, sir.
Yeah, so I'll give you 2 minutes, just work it out, work this problem, and then I'll provide the solution. I'll give you 2 minutes. 6:18 now, 6:20 I will start working out. And try to work in these notations only. Don't try to expand them. We Because the second problem which we are going to do, we are going to compactify all those notations and just do the proof of what was done in the video.
In this, the partial derivative of x comes only in this phi, right? The function phi.
Partial derivative of x comes in both AI and also in phi. It's there in both. Yeah. Okay, let me do along with you. Okay, first is 2L by dou x dot I, which is equal to Pi. It is equal to uh, mm, and let's say dot plus E by C x, right? And you have dou L by, now you take ddt of this thing. So you have your ddt dou x is equal to dou L by dou x, which implies ddt of this thing is then xi double dot plus EYC ddt ki x. Dou L by dou x is minus c dou phi by dou x plus EYC xi dot dou ai by dou x. Okay, now what to do? Any this thing? Any ideas? I want to write this in terms of E and B. That's my goal. So I have to use this thing here. Where I've written J like this, right? It means that they are being summed over, okay? So this is x dot j dou ai dou xj. Sorry, I missed an I here. So this thing, that lower and upper, this means that it is being summed over. That is our notation. So or repeated indices are summed over. I'll write here notation. Let me just change this. I'll put this above. I'll put this. Put this also above. It's fine because we are not doing special relativity here. So it is all right. So we find that force is equal to minus E. Now this thing is nothing but now our electric field is nothing but the ith component of the electric field E is dou phi by dou xi. This is because this is gradient of phi. This is just I've written this in the component form. That's all. So I'll put this on the other side. So you have EEI plus E by C x dot J. Okay, this is what we get. And we can even take this out common. So we'll finally get the same thing. Oh, there's nothing here. I'm just taking that common because there is some structure hidden there. So this is what we have. And what is this term? We need to figure this out. So if you see this, I'll write this in a different way, okay? Hello, Daksh, you can follow me, right?
Yes, 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 yes. So,
So I will write this term a bit differently. I will write delta J. This is Kronecker delta. So okay, I will write it as follows. J A delta I B minus delta I A delta J B. And I will write this as del by del x uh, B A. A. Are you fine with this step, what I have done? Can you understand the step? Do you understand this step, Daksh?
like you're picking x and a of each component with the canonical delta. Like,
Yeah, yeah. So if I put this here, A, you will get the same term, this term only. Can you see this? Because A and J, Kronecker delta means you are going to get, for only J equal to A, this term is there, right? Correct.
yes, yes, yes. Right.
So I'm introducing some auxiliary variables. Okay.
Okay.
Now, yeah. Now this thing can be written as, this is the trick. This thing can be written as, this thing is nothing but epsilon. I'll introduce a new variable here. A, B, K, epsilon, I, J, K. Okay. All right. So this thing, right? How to check if this is true? So this is actually an identity. This thing can be written as this thing, or this thing can be written as this thing. Okay. Did you know this, Daksh, beforehand?
No, I haven't seen this identity before.
You haven't seen it. The way to check it is like this. Okay. So fix a k. Suppose k is 3, right? Suppose pick the epsilon a b k epsilon I j k. We are going to derive delta a I derive delta b j minus derive delta a j. Okay, just pick k is 3. And now if k is 3, ij should be 1 or 2, right? Because if you put 3 in ij or ab, ij and ab, then your this thing is nothing but 0. Okay, correct. So okay, if you put a is 3, a, a is 3, and so this part is 0, well, you can just, the best thing is you can just, okay, you take this as homework. You can show it. You can show it for one. Say 3, take k is equal to 3, and I and j as I take I equal to 2, j equal to I equal to 1, j equal to 2. Then you have something like 1, 2, 3 times AB 3. Hmm. Okay. Now 1 to 3 is nothing but 1, right? Now if your AB is, yeah. If so, now how can you make 1 this side? If your A is also equal to 1 and B is also B is equal to 2, then you directly have delta AI, delta BJ here. Okay. Now if you have, yeah. Now if you want, this is 2, 1. Okay. You can have the other part also, the minus sign, the other part also, right? Now this can still be non-zero if you choose A is equal to 1 and B is equal to 2, right? But this time the answer will be minus 1. So you have to add this thing also to BI. Okay, this is for the minus 1 part. This is for the minus 1 part. This is for the plus 1 part. Now let's take AS3. AS3 and I is also 3. Okay. So our thing is like 313, 313. Okay. Then this part is 0. Now look at this part. 3, 3, 3. Bj is also 1, 1. Delta Aj is 3, 1. Okay, there's some mistake over. 3. Well, did I do some mistake? Oh, sorry. Okay, sorry. The k cannot be 3, right? K has to be a summation. So you will get it to be 0. You understand? I'm sorry. So the identity is gotten like this, okay? Epsilon AB 1, epsilon ij 1 plus this k means summation, right? AB 2. Epsilon AB 3, epsilon ij 3. Now if you take 3, 1, 3 here, so A and B are 3 and 1. And this is also 3 and 1. So this is 3, 1, 3, 1. This is 3, 1, 3, 1. So this is 0. 3, 1, 2 and 3, 1, 2. You are going to get 1 from here, right? 3, 1, 2 and 3, 1, 2, you are going to get 1. Right? And 3, 1, 3 and 3, 1, 3, this is going to be 0. This is also 0. This is 1. This is 0. Now put this in the identity. Identity says that you should have delta A J, AI Bj, right? So A is 3, I is also 3, B is 1, J is also 1 minus delta 3, 1, delta 3, 1. From this identity, from left hand side, it's also giving you 1. So it matches. Okay, this is the way to check. But you can derive this thing also, that this is equal to this. So I'll write this thing as like this. And the reason for writing this like that is I want to use some identity of curl of the vector. Now this part is nothing but curl of a vector. Okay. This is curl of A, the component of eighth component of uh, the kth component of curl of A vector. Okay. This part. This is an identity. Did you know about this identity?
This idea.
Was there a half or not in the front? No half, right? No, there should not be a half. No, there won't be any half. Yeah. So this is curl of A, and you Write it as following. J, the curl of A is K component. That means that term is nothing but B of K, right? The kth component, curl of A is just B. So this is this is giving you the kth component of curl of A, which is BK. Okay. Fine with this? Hello.
I see.
So curl of A is B, right?
Curl of A is B.
So we found that this term is nothing but the kth component of curl of A vector, which is the B vector. And the kth component, I'm calling it as BK.
Okay.
Okay. So BK epsilon IJK. And this is nothing but B cross B, right? This is the ith component of B cross B, because this is V and this is B. So this is nothing but, if this is to be written in vector notation, this is the ith component of that. So we get force, which is this part, mx double dot I, in the ith direction is equal to electric field E times electric field in that direction by E by C into velocity of the particle cross B in that direction. Now taking all the components and writing this equation in vector form, we have this equation. Now what is this equation? Do you know what this equation is, Daksh?
The electrostatic force.
Yeah, your Lorentz force equation.
Lawrence.
Okay. So you're fine with this, right? Any questions, any doubts?
No, it's fine.
It's fine, right? Okay, great. So I'll give you one homework regarding this. If you find time, do it. This is a small thing. You can try to, you have got Lagrangian. You've got Lagrangian. Find Hamiltonian. It's standard. Okay. B. So, no, leave this. Find this thing. Okay. Find this thing. This is interesting. Xi dot xj dot. This should come out as some factor into dk, I guess. The other this thing. This should come out as magnetic field. Okay, some component of magnetic field here. I guess the other component. Okay, let me just take my solutions. Yeah, you'll find the other component. And the constant is something like this. The m square c. Check this. All right. And this is actually, you get this to be, this term to be like ijk. If you want an epsilon, put this. Okay, try doing these questions, and yeah, I think you'll have understood a lot of it. Now let's go to field theory. Okay, field theory. Hmm. So the question number 2, which we'll do, is taken from this book called Schroeder. It's the second chapter of Schroeder, and it's the first question of that one. But before doing that, I will discuss Green's functions now. Okay, I'll discuss Green's functions and how to find them. All right. Yeah. So given a Lagrangian, and this is field theory Lagrangian, so it's called Lagrangian density actually, which is equal to Lagrangian density. I'm going to write to you. Ah, no. I think we should do this question beforehand. So you are familiar with the concepts of four vectors, right?
Yeah, kind of dealt with this for vectors, yes.
So you are good with manipulating symbols?
Might be a bit rusty now, but yeah, I think I can follow.
Okay. So you know what this means? Where, or if you want, I'll write this as this. F is the electromagnetic tensor, where F mu nu is 0, 0, 0, 0. And what's
Uh,
your E, right?
One is the transpose of the other, right? I mean,
One is the
transpose of the other, right? I mean, F
not
superscript
transpose,
UV.
inverse of the other. But yeah, it comes out to be.
Tran-
Mhm. No, the upper symbols mean upper AB means lower AB's inverse. It's not the transpose. If you have F mu nu, transpose of this F mu nu is this. Mu nu transpose is equal to the transpose of F mu nu. You need this now. Suppose if you are looking at F, if this was F12 and you want this now, so you just have mu. Am I right? Okay, the upper symbols means that it is a this thing. It may so happen that this is equal to a BA or something like that, but it's not the transpose of the other in general. I'm saying in the tensor sense.
I've got it. It should be. It is inverse, actually. That's what you're saying, right? You're saying it is inverse, right? Like F.
Yeah.
Okay. You may continue. You may continue.
Oh, wait. Like I'm not saying for this case or this. In general, in tensors, what you do is you can define it in a different way also. Actually, I'm wrong. Okay, I'll tell you what I meant to say. I'm sorry about this. F mu nu is not this, but F mu nu is actually this, in this case. Is pushed. It will be FAB. Okay, this is correct. This is how you raise and lower for this case. This is right. Hello, you there?
I got
Okay, this is for this case. Okay, this is for whenever you are dealing with special relativity. Remember this. This is coming because we are doing special relativity here. Because in our theory, we have this relativity, this symmetry, Lorentz symmetry. But in general, if you go to GR or something like that, your G mu nu, G mu nu, it's actually the dimension of this, like dimension of the matrix, if you want to say, this G mu nu matrix. The metric, if you have, that's that. Okay, leave this thing here. So, yeah, you can always think AB to be the inverse of, even if you have FAB, you can tell this is the inverse of FAB, but in the sense of, in the relativistic sense. That means, like, it has to obey the symmetry of this thing. This is what I mean to say. It's not just metric inverse. Okay. Forget that. Let us go to the Lagrangian density, which is this. Let me get this right. The factors in front. I think there is a minus 1/4. Just check. Okay, how to go about this? You have to first find the Euler-Lagrange equation. Hello, Daksh, are you there?
yes, sir.
Yeah, how to do this?
So you have to find Lagrangian from it, like integrate with.
No, yeah. Lagrangian, this is the Lagrangian density I have given you. Okay. And this Lagrangian density is function of the fields A vectors, this electromagnetic potential and their derivative. Okay. And this is equal to, as I have written before, F mu nu plus A mu J mu, where F mu nu is equal to D mu A nu minus D mu A mu, where D lower mu means ddx of mu. Are you fine with the notation, or is there some doubts?
No, it's not.
It's fine. You're clear.
Yes, yes.
Okay. Then let's. Okay. So how will you find this thing then? How will you find the Euler-Lagrange equation? Can you just tell me?
Uh, till now, I
In
was like writing the action by integrating the Lagrange density with both position x and t, and then minimizing it. What was I doing?
yeah, but that will just give you the Euler-Lagrange equation, right? Minimization of action will give you Euler-Lagrange equation. So you can just directly use the Euler-Lagrange to do the minimization procedure. Are you clear on that?
Yeah, I'm clear to that in like, but I don't remember the Euler Lagrange equation for like what fields, right?
Fields.
Oh,
Hmm. Okay. So the Euler-Lagrange equation in general case, okay, is dou L by dou X. If the Lagrangian is a function of X, X dot is like this, right? Hmm. Now instead of X dot, your Lagrangian, the same function. Now this L is the curly L is some function of say A, and A can be many things, like A can have many components. This X could have many components. That is why we'll do it by I, the ith component, right? So you understand this thing, right? The first line which I have written, this is in classical mechanics.
yes, yes. I'm familiar with that.
Uh-huh.
Yeah, I'm familiar with that.
You're familiar with that. So
Uh,
now I just want to put this. If I have this, what would I do? Can you just, like, tell me how to do it? Can you just think, make correspondence with this and try how to write the Euler-Lagrange equation? This is a way, I'm teaching you the way.
or do nu do mu l
Dou mu L.
curly l is equal do do
No,
t.
no, no, no. Like, look. What has happened? I'll tell you. Look, this x dot is what? Okay, this is this Lagrangian. Okay. Now I will write x dot as dou zero because dou zero is equal to d dt or dou t. Hmm. Xi. Now we want to go from here to Lagrangian Ki, which is curly now. Zero has mu Ai. Hmm. Tell me. So this will just be dou curly L dou Ai is equal to d dt you have, right? D dt you have. So in this field theory, this becomes, because mu can be spatial, this ddt you had because you had only time derivative here. Now you have mu's also here. So this has to be, this can be any derivative. So this will change as dou x mu dou L dou mu a I. Okay, got it.
Uh,
Got this equation? Can you make parallels with this equation and just say if you are satisfied or not?
I think it looks good.
Looks good, right? Now your L is your L is this equation. Now use this and put it there. So dou L by dou AI is nothing but here I is can run from 0 to 3, okay? 0, 1, 2, 3. It's like we are treating it as a Greek index only. So this can be J, I, right? Because F mu nu only has derivative of this thing. If you remember, F mu nu only has derivative of A. So this is only, this gets differentiated and you get Ji is equal to dou x mu minus 1 by 4 dou F mu nu F mu nu dou of dou mu AI. Now we'll just look at this term. And we'll apply chain rule, okay? Now one. So see, there is this is being summed over, right? F mu nu, F mu nu means F00, F00 plus F11, F11 plus like this till F33, plus whatever, all the components, F01,
One,
F01, okay, whatever it is. So this is being summed over. So, and I'm using the same mu here. So I'll change the index of this one and write this as alpha beta. And I'll put this I down. If I put this I down, I'll also have to put. Okay, let this I be a later. We'll see what happens. F mu was dou alpha a beta. Hmm? So now you want to match this with this, right? So you want this alpha and this beta to be down. And there you're going to use this thing. Eta alpha P suppose. So this is dou P. This thing is nothing but this. Similarly here, beta P dou P. Yeah. So if you differentiate here, alpha P, now observe, if this is only if this is mu is equal to P and I is equal to beta, then only this will be non-zero. You'll get a 1. This is like differentiating dou of x dot by dou x dot. Okay, this is like this. That is, I'm writing 0 x dot I, x dot I. Then only it's 1. If you have dou of x dot 1, x dot 2, for example, x1 is x and this is y, then this is 0, right? Because they are independent components, right? Of the in the Lagrangian, they are independent components of the configuration space. So this part will only be non-zero when your p is equal to mu, and will be very careful about notations, and I is equal to beta. Okay. Similarly, this part, your p is equal to mu and I is equal to alpha. So you will get, now Dirac delta P mu, this can be contracted and written like this. This can also be contracted and written like this. So you get something like this. Now can you do the same thing for this part? Can you do it fast? This is for the other part. Daksh, can you do it? And tell me the
I'll,
answer what we should get.
I'll try.
You know what this eta is, right? This eta is this matrix.
The diagonal one, right? One
Yeah.
minus
Yeah,
one
minus.
minus one.
Yeah. Do it and tell me, okay? I'll just charge my this pencil. So charges out.
if subscript alpha beta is similar to f superscript alpha beta, but
The
uh,
indices are down.
that's
So do alpha should be lower, A beta should be lower.
it.
Earlier you had everything as upper, right? This time it will be lower.
So, it should be similar to the other one. Just this eta eta is applied on this a this time, right?
What?
It should be the final answer should be similar, but in intermediate step, this eta should be applied on a, right, to make it.
Ha, correct,
Uh,
correct. So you will get alpha mu beta I minus mu, right? Or am I wrong? Just check. No, this is wrong. You will get this.
this one should be
This should be the answer. Just check fast.
okay. That will be.
Yeah, you are going to have to use that only. So you will use this. Let me do it very quickly. Okay, let me do it very
Okay,
quickly.
okay.
In 1 minute calculation. So that means you have alpha, beta, and beta alpha below. That is like this. But you want those betas and alphas to be above. So say some p, and you have here, here you have eta, p alpha, eta, p beta. Correct?
Does this
And now,
post multiplication and pre multiplication matter here?
what?
This, uh, multiplication of eta, like should I post multiply it, pre multiply it? Should it matter? Like,
No, it won't matter because no, when you are writing eta pq, right? So this is the notational problem. Okay, when you are writing eta pq times ap, something like this, what you mean is the eta pqth component of eta matrix. So eta 1, say this is say aq. Okay, so if you want aq, if you want a2, this means you want eta 1 to a1 plus eta 2 to a2 plus eta 3 to a3 plus eta 0 to a0. Okay. Now these are components, and these are also terms a1 eta 1 to term of the eta matrix. So eta 02 is not a matrix. Eta 02 is a number. So it doesn't matter if you write it here or write it in the front. Okay. But many books write as eta mu nu as this matrix, but when you write this, it is already meant. It is already, we know what this means.
Got it. I thought it was matrix. Sorry.
No, 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 no.
That's elements.
So you have, so alpha mu ei minus delta beta delta e. Am I right with this one? Oh, actually, you are going to have this term only. So this is also wrong. You're going to have this. Sorry, you're not going to have this also. You're going to have this term. So delta pi can be written as, this term can be written as eta I beta and this term can be written as beta pi eta I alpha. Okay, my mistake. This is beta. This should be your answer. Did you get it?
I couldn't complete it. Yeah. Just going to.
But you know how to solve it, right?
Yes, yes, yes.
Okay. Now you just put it in this equations. Substitute in this equation. The first part is mu delta beta I is delta beta mu delta alpha I is of alpha is of alpha beta beta mu alpha beta I. So if you use it here, you'll have beta alpha mu. So mu will go above and beta I, and I is like this. Minus, if you use it here, mu will go above and I. Okay, there should have been a plus sign here. I made some mistake. Got to search this mistake. Oh yeah, sorry. I found it. So if you put this in the first term, what will you get? Your mu will go above because alpha is here. So mu and beta will be I, so mu then I, minus, if you apply this in the second term, you'll have alpha is in the first term, I then mu, okay, plus similarly here, f f mu beta is eta I, so I minus f I then mu, okay. Now you want this to be in the same, like if this is raised, you want this also to be like this only. This also to be like this only. To do that, what you'll do is in this second term, you'll do a change. That is, I'll write this term again, and here I'll continue. The first term is f mu nu I minus beta mu delta alpha I f alpha beta plus the first term is f mu I minus f alpha beta mu beta k alpha. Now I'll do this change. I'll change the index of this alpha beta. So this will be beta alpha because we know this is using alpha beta is equal to minus f beta alpha minus, I'll do the same trick here, beta alpha alpha. So we get f mu I plus f mu alpha I plus f mu I plus beta is mu alpha is this. So I will get 4 times f mu I. Okay. Therefore, Ji is equal to del 4 times 4 times f mu I, which is equal to this. I'll write in component form. This cancels. D mu f mu I. Okay, why is I down? I should have been up. Okay, I should have been down. I don't know why I wrote it. So this Ji is down, right? Okay, so this is our equation of motion. Okay, can you hear me?
Yes, sir.
So we got our equation of motion as minus del mu I is equal to Gi. Now what you want to do now is to find this thing. Is to find, okay, now I'll give you f alpha beta and f this thing. Your job is to find in terms of E vector and B vector. Is there someone here? Response. That's very okay. And if mu is given to you as this, okay, I'll give you both of mu nu. Mu nu is this.
There should have been the C term, E by C or something, right?
Oh, leave that, leave that. C is one for us. If you want that C, right? That
Oh, like we
C
had
will,
normalized it. Oh, it's fine.
yeah. Hmm. And if mu nu is, what is F mu nu? Lower mu nu. It is Ex, Ey, Ez minus Ex minus Ey minus Ez 0 minus Dz dy. This is Dz 0 minus Dx 0 dx minus dy. So look, this is not the trace, not the transpose of this term. This term is not the transpose of this term because look at this part clearly. This part, this and this, they are same. Okay. So if you are to raise this index, right, the ith index, you're going to have something as like this. Gi. And let's assume that the components of Ji are rho and J vector. Okay. So now what we'll do is we'll write for I equal to 0, the equation. So we have D0 as 0, 0 minus plus D1 if you want 0 is D2 means the T0 as D3 30 is equal to J0. So the upper J0 should be with a minus rho like this. Huh? Let us just check it. So F00 is what?
Zero.
F10 is what? It is upper 10. Hmm? Hello?
Zero. EX. EX.
Uh-huh. What did you say?
EX. EX.
EX. F20 is EY. F30 is EZ.
Easy.
Right. So I think there should be this minus sign. Okay, this minus sign and this minus sign will cut. So this is 0. This is 1 is X for us. dx ex plus dy ui plus dz ez is equal to rho. So this is nothing but divergence of E is equal to rho. That is del dot E is equal to rho. So this is what? Which law? This is Maxwell's equation. Gauss's law, right? This is del dot E is equal to, oh, sorry. Correct. Correct or wrong?
Correct.
Hmm. Now let us quickly do for I is equal to 1, 2, and 3. Okay. Then you are going to find, so I equal to 1.
I'll try
This is number
to.
1. Yeah, do it fast. Do G0, F0, 1, D2, F1, D3, F3, 1, is equal to J1, minus J1, with the minus sign overall. And this is equal to this minus D0 EX plus D2 DZ minus D3 DY is equal to minus J1. Similarly, if you do it for 2, you will just minus D0 EY minus D1 DZ D3 DX into 2, 3. So we have 1, 2, 3. And you are going to add all of this. Okay. If you add all of this, like component wise add in, okay. So you will write what I mean to say is you'll write this vector equation and add them. So you will have minus j vector is equal to minus d dt of e vector plus this is curl of b. Okay, you probably find minus curl of b, I guess. Minus curl of b. Curl of b will have curl of b means what are you going to get in curl of b? Curl of b means you're going to have something like cap y cap y cap x cap z, and this should be dy dz. So let's see in x part d2 bz d3 by 3by. So this you are going to get as minus curl of b. Okay. Okay, I verified it. You verify this thing and you realize that it is minus curl of B. So you have minus J vector is equal to minus del del T of E vector minus curl of B. So you will get curl of B as, so is there a mistake in here? There is a mistake, I guess. This some signs are not matching, right? Let me just check. I think there should have been a plus. And where is this plus? So what is the mistake I have made? 0, 1, 2, 1, 3, 1. 0, 1 is 0, 1. Oh, yeah. Uh, 0, 0. Oh, sorry. 0, 1 is 0, 1 is minus AX, right?
Minus 8.
Yeah. So that part is fine only. 0, 1 is minus EX. And curl of B is also correct, right? Is this plus curl of B?
In J1 it is positive, right? It's correct, right? Positive curl
Huh?
of B, right? Like,
Yeah, yeah, yeah. Curl of B should be, this is positive.
yeah, but in the final equation you wrote does minus curl of B.
Yeah. So curl of B goes this side and J will go this side. So there's a plus. There should be a plus here. Right. In the Maxwell's equation, this is plus, right? This is plus, right? 0, 1, 0, 1, 2, 1, 3, 1. Oh, no, no, sorry. 0, 1, and this will be 0, 2, this will be 0, 3. Oh, what is the mistake? Getting difficult now. Once again, this is written B2Z. Yeah. Oh, this is plus. You were saying this, right? Yeah, I wrote a minus. I'm so sorry. Oh, thanks. So this is a plus. This is a minus. But here I'm getting a minus. So I'll just change the definition of that formula. Wait, if I make this to minus j, will there be a problem? No, I guess not. Hello?
Like
If I
minus
make this
Jensen.
to be minus j vector, will there be a problem? No, there won't be any problem. Mm-hmm. So if I make this minus j, so this is kind of a manipulation, okay, but this works. Nothing has changed. So this will be plus j. So everything will be plus. Okay. Hello, you there?
Yes.
This is the Ampere's law, right? Okay, this is one of the Maxwell's equation. So see, from the equation of motion, so equation of motion gives us two Maxwell's equation, which are del cross B, okay, and del log E is equal to rho. Okay. The other two equations are del cross E equals minus del B by del T and del dot B is equal to 0. Now I want to point you out to something, okay? So these two Maxwell's equation, which I'm writing as equation 2, and these two Maxwell's equation 1. Equation 1 has source information. That is, it has rho and j in its equation. Equation 2 has no source information. That is, no rho and j. Hmm. Since this has no source information, this should be intrinsic to the tensor from which it is built. And this equation actually, these two, equation number 2, comes from Bianchi identity. Which is the identity? This. You do the cyclic permutation of this, okay? Mu So if you were to put this thing, now this is very tedious job. So lambda equals 1, mu equals 2, mu equals 3. Then you'll get lambda f23 plus d2f31 plus d3f12 equals 0. Calculate along with me, okay? Minus d1 dx minus d2 dy minus d3 dz is equal to 0. This is nothing but divergence of B equal to 0. Got it?
Yes, yes.
And to find this thing, you use lambda equals 0, mu equals 1, mu equals 2. This will give you an equation d0 f12 plus d1 f20 plus 2f01 equal to 0 equal to minus d0 dz. This I'm writing here as A. Lambda equals 0, mu equals 1, mu equals 3. This will give you minus d0 dy plus lambda equals 0, mu equals 2 plus 3. This will give you minus d0 dx minus d2 dz plus d3 dy. A, B, and C. Look at these three equations. You have d0 bx, d0 by, d0 bz with a minus sign. That is derivative b vector. And d1 ey minus d2 ex. So that is minus del cross e vector. So you get the equation. This is your fourth Maxwell's equation. So this is how. So Daksh, you are clear?
Yes, yes.
This is how using the Lagrangian you find the Maxwell's equation. Okay. Now, what we are going to do is we are going to study a little bit about stress tensors. So it has been motivated in the book, in the instructor's book in a different way, and I'll do the thing in a different way. Okay. So we'll do stress tensor in field theory, and I'll just take the notes out, and I'll give you a homework to calculate the stress tensor in this case. Okay. Noether theorem in field theory. Suppose there is a transformation. There exists suppose there is a transformation of the field I am referring as phi, phi x as phi I. Ith field changes this. And due to this, the Lagrangian density, which is this, changes as del plus delta L, where delta L is equal to some divergence of a function, divergence of some function g mu. G. Divergence of some function g. Okay. Where g is this function of the fields. Now Lagrangian density, which is a function of fields, changes as becomes phi I plus delta I phi del mu phi I plus then this is what of can be written as phi I plus here this I, it means like they are being summed over. Okay. Plus higher order terms, which we'll ignore. These terms we'll ignore. Up to order delta, these are the terms. Therefore, delta L, which is equal to L of phi plus delta phi comma dot, which is minus L of phi comma dot. Okay, this is equal to do L by do phi I delta phi I now I'll do some chain rule. Minus do mu sorry, not chain rule, but product. But the product rule actually. Plus do mu fine. This is fine, no? This much is clear.
Yes, sir.
So this is what? This is the Euler-Lagrange equation. You take delta phi I common, you're getting the equation of motion. Hmm. And if you use the equation of motion, we have this part to be 0. This implies delta L is equal to dou mu, dou L, dou mu phi I, delta phi I. Okay. Now I'm saying that my delta L itself is some kind of dou mu G mu, right? So I'll take this common and I'll find that dou mu, dou L minus G mu is equal to 0. Okay. This is my conserved quantity, which I'll tell as current. Therefore, G mu is equal to okay. Now let's do something. Let's do an example, which is called the stress tensor. Suppose you do a space-time translation, that is, then you have the field as the new field is equal to the new field is defined as phi of the new field is defined as phi prime phi prime, which is defined as x prime mu plus epsilon mu. No, no, no. Phi of x prime is equal to phi of minus epsilon mu is equal to phi of x mu minus epsilon mu d mu of x mu. And we'll look at only this much term only. Okay.
Why do you want this field to be conserved? Last time
No,
we
we
just
are.
last time like we wanted this Lagrangian to be conserved, right? The
What? I didn't understand. No, no, no,
like
no, no. We under the transformation of the field, okay? Under the transformation of the field, the Lagrangian changes somehow, delta L. And the delta is L is a total derivative term. Yeah, total derivative in the sense this time in field theory, it becomes some divergence of some function. Suppose it is like this. Hmm. Then you will find a conserved quantity, which is this J mu. Last time also we did this only. Instead of phi, we had x, and xi went to some xi plus delta x. And this delta L changed as edt of some function f. Okay. Any more doubts?
Uh, the, like the last equation you wrote, right?
This equation?
Like, why do you want this to be conserved? Like, is it a
What to
condition that
be?
we apply, like the field, the new field form?
No. The new field form is not conserved. Look. The idea of
Oh,
field
it's
is not
it's pi
conserved.
only. Okay. I thought it was pi prime x prime. Okay.
No. This phi only, but it's
Oh,
looking.
okay.
We are evaluating phi at a new coordinate.
Oh, okay. That's fine.
See, look. What we are doing is like
And understood. I thought it was pi prime. Like pi also changed. We wanted it
no,
to
no,
be
no,
the
no,
same.
no,
Okay.
no,
That's
no.
fine. Got it. Got it.
Oh, I was giving it a new notation. Okay.
Okay. It's good to do. Thanks.
Hmm. So you are going to have this, and this is how your field changes. Suppose we make the space-time translation, space-time, this is x mu plus something like this. How does your field change? That is the question which we want to ask. Hmm. That means to say, suppose your field has some value here, which is phi of x. Hmm. Now what we did is we
We
made
change the
some space
position.
slides. Yeah, we changed the position. Say here, x mu, this is x mu plus epsilon mu. So I'll do plus. How does the field change up to some order?
Okay.
Then you will evaluate using like Taylor series, right?
Yes. No,
This
no,
is only what I have done.
I thought like we are changing the frame of reference and we shifted, we changed the form of pi also. Like we are writing
No, no,
new
no, no, no,
pi
no,
prime. That's why I asked. Oh, it's fine.
no. This can be defined as my new. See, this is this, right? This I can define as my new phi prime of x. That is what I was trying to write. This is a new function, new field. This is a new field at x, which is defined as like this. The old field evaluated at x plus some one, say.
Okay, it's
Or like you understand, right?
yeah, I understand.
Hmm. So this is your change in the field. Therefore, delta phi, I'll drop the epsilon. Delta phi, uh, delta phi mu, I have to keep them. Leave it. I'll keep the epsilon mu. Okay. See. Okay. Hmm. Now, Lagrangian inside the action, okay, Lagrangian, if I write the action, Lagrangian is a function of the fields, which is again the function of the space-time points, right? So we will again think Lagrangian to be a function of x and Yeah, we'll think Lagrangian to be a function of x. Hmm. All right. And now we'll do the transformation here too. And when you do the transformation, you will find some Jacobian because you're changing this measure also. Correct. Are you getting what I'm doing?
Like Jacobian comes when only we change the frame of reference. Like
Yeah, yeah, yeah. Actually,
here we
you are
change only the
changing.
position.
Yeah, you are changing the position. Look, look. What is happening is now I'm writing Lagrangian is a function of x, right?
Mhm.
Look, Lagrangian is not a function. Lagrangian is only function of field phi and derivatives of
Derivatives
phi.
of phi.
Hmm. When you put it in the action, so what I mean to say is Lagrangian. So in classical mechanics, let's go there. Lagrangian is a function of x comma x dot, right? And when you put it in the action, you want to have a trajectory x of t. That is why Lagrangian, when you put it inside the action, becomes x of t, x dot of t, right? Now here you can think this as t L of t. Hmm. Now you do the time translation, t plus epsilon. Say t prime is equal to t plus epsilon of t. It's some function of t. What is the Jacobian here? It is dt prime by dt is equal to 1 plus d epsilon by dt. Okay, so I will write this as epsilon times L some function. Epsilon is some parameter, okay, function of t. So that I can take this epsilon as. Hmm. Then my action in terms of new trajectory prime of t will become integral this dt prime L of t prime. Okay, this will give you integral 1 plus epsilon df by dt times dt. I'm writing dt prime. Hmm. Times L of t will become t plus epsilon f of t, right? So this will be integral dt plus L of t plus epsilon f of t dl by dt, right? Correct.
Yes, yes, yes.
So up to first order. Hmm. Up to first order, what are we going to have is two terms.
L of t and
Hmm?
nothing.
dt L of t, this is the first term, is epsilon Hmm. Hmm. All right.
Yeah.
Now what you can do is uh, I want to get rid of this term. How to get rid of this term? Minus this.
Like differentiate,
Hmm.
but like product rule you can use, right?
Yeah, yeah. Then you'll get something like S. This is
Uh,
original plus epsilon dt of f times L. Hmm.
I think
The other
another
part
term
cancels
term
with
to
this.
cancel.
Yeah. Now you choose this f to be some constant. Hmm. Wait, if I were to choose this f to be some constant, then the Jacobian is just one. Yeah, yeah, yeah. So I actually should have started this f to be some constant. Okay. So this f is so I made some problem in the argument, but I'll choose this f to be constant. This is a constant. This thing I'll do. This translation, right? I'll do a constant translation. Okay.
Okay.
If I do a constant translation, my delta S is some epsilon pp. Epsilon f is a constant, so it came out ddt of
DT.
L of t. Okay. So my Lagrangian delta L is ddt of L of t. Hmm. So my Noether's theorem says that under this change, x of t prime, which is equal to x of t plus ddt epsilon dx dt, right? Epsilon x dot. Therefore, delta x is equal to epsilon x dot. Hmm. So I'll drop this epsilon also because it's not important. I have found delta x. So remember, Noether's theorem used to say that you will have a conserved quantity J, which is equal to dou L by, in classical mechanics, Noether theorem, okay? Dou L by dou x dot times delta x minus this function, whatever ddt of whatever function that is, minus f. So in our case, dou L by dou x dot is what? Dou L by dou x dot is by definition p, right? Right or wrong?
Yeah, correct.
And delta x is x dot. And f in our case is L, because this is nothing but delta L is, that is correct. This, what is this thing?
Hamilton.
Yeah. So what I wanted to say here was that in uh, in classical mechanics, you have this when you do the time translation, the Hamiltonian is the conserved quantity. That is what I proved right now. Okay. You can do the same thing here with constant space-time translations. And that was what I was trying to do.
Uh-huh.
So next class, I will show you this thing. Classical mechanics, constant translations correspond to H, field theory, constant space-time translation correspond to stress tensor. Next class, I will. Okay. Okay, let's end it here.